do the reciprocal when we go to the impedance form, because that 2 millifarads becomes negative j over omega times c. So there we already did the inversion. So once it's in impedance form, you don't invert anything or anything like that again. You just do your standard as if everything was a resistor. Right, is that clear? I just don't want anybody going in and saying, well, that was a capacitor, so I added it in its inverse or something after you've already done phasor form. You don't need to do that because you take care of it here. So again, series with this whole combination. Right? And so it comes out as a complex number. Right? Not too big of a deal. So again, I could plug this into a circuit. I could plug this into MATLAB, and those 5 elements now became one little box with a complex impedance. Really simple by comparison. Right? That's the end of chapter 9. So, chapter 9 sets the stage for us. In chapter 10, we're going to go into all the stuff we did in chapters 3 and 4. So all of we kind of pretty much covered nodal analysis and mesh analysis, but we'll do some more of that formally in chapter 10, as well as reviewing applications of superposition and linearity, all of that kind of stuff with the phasor representations. So it should be pretty straightforward for everybody because it's kind of a review of everything we've done before with DC. We're just going to revisit it and make sure that we understand any small nuances of dealing with it in the frequency domain. So you have a chapter 8 homework that's due this Friday, right? Have you guys started looking at it? Are there any questions? Should we go through any of the problems from chapter 8? What do you think? No? Everybody's happy with those? I mean, again, most of those you should have done last semester, so it's just supposed to be a review. If that's the case, then for just a couple of minutes, I want to I do just want to review a little bit of using MATLAB. Did it launch is the question. I hate Skype spam. I can just quit that actually. MATLAB likes to take its sweet time loading up. So. It's getting to that stage where I'm going to have to reload I can feel it. I need to refresh my Windows and start from scratch. It's been 2 years or so, 2.5 years.
Fresh reformat.
Yep. Does a lot of good.
It does. My desktop.
So, all right, well, all that's loading. So what I want to do, though, I definitely want to show you guys, to remind you, how to use like the Wye-Delta transformation, and we'll do it with complex, all right? And we can show a few. I mentioned some of the commands. I know, Justin, in fact, you asked about that on Monday's class. Some of the commands for transforming between polar and Cartesian coordinates, things like that. So let's just write down, we'll do it in the format we're kind of used to seeing. So we'll do a Wye-Delta combination for something like this, right? So I've got an inductor, a capacitor, and a resistor, and I want to turn those into three impedances in a delta instead, right? So how can I do that? So let's just assign these guys some values. just to save myself the headache, I'm just going to write down some complex values so that I don't have to worry about it. Again, I know an inductor is a positive J, right? So let's just say that that's J10. The capacitor should be a negative J, so we'll make it J5, I guess. And then the resistor is just a real number, so let's say it's 3 ohms. Okay? So these numbers are as ugly as any other numbers you could get, right? There's nothing special about them, and there's no guarantee that they're going to work out neatly or nice or anything like that. And so how would I, do a Y to delta conversion on these? Well, again, I don't even like to remember those stupid formulas from the book, right? But you'd have to do, so from the Y to the delta, it's like, what is it? Oh my gosh. So it's like, if it's this one, so I think it's like this times this, plus this times this, plus this times this, divided by that, gives me this one, kind of a thing, right? But at any rate, what I do remember is that whatever order, when I put them into MATLAB, whatever order I have them in, so in this case, like, if this is 1, 2, and 3, it's going to yield elements 1, 2, and 3 in my array. Right? So that's the one thing that you do need to remember to use the Wye-Delta conversion scripts in MATLAB, because you've got to know what element of the array corresponds to what physical element that you're talking about, right? So now that we're up and running, again, if you haven't done it already, you should make sure that that M file is loaded into your folder that's in, that you have a path set to that folder, or you've copied it into your MATLAB directory in your My Documents. So I have mine over here, and so you can see we're going to do a Wye-Delta. I see the delta Y. There's the Wye-Delta. So if I want to pull it up just to show you guys. So here's the Wye-Delta. And the elements of the delta, yep, it's y1 times y2 plus y2 times y3 plus y3 times y1 divided by y1. So I actually did remember it correctly, right? Yay. Right. So to run this script though, it is a script. So I need to have y defined. And then it will give me delta. So it's not written as a function, so I have to just go back to my main screen. And the first thing I'm going to do is I'm going to define the matrix Y, right? It's a matrix, so it's inside of square brackets, and it needs 3 elements to that matrix. Those 3 elements are my elements 1, 2, and 3 from here. So the first is J10. And again, MATLAB does recognize J10. You don't have to use the multiplication symbol. Actually, I think it's 10J. I think you have to have the J after the number, after the coefficient, or it does get confused. And then element 2 is negative 5J. And then if you want to be careful, you can always just put the multiplication symbol in. The third element is 3 ohms. Right? So I've separated each of those elements in this case by a space. You can also separate them by a comma. And use parentheses. Parentheses are your friend when you're dealing with complex numbers, right? Because you need to keep that number together. And so if you have to start dividing things or whatever, keep them in parentheses. So if it were more than, if it were 2 elements, I would just suggest putting each one of these guys, into parentheses to make sure that you know what goes with what. And you don't accidentally have a space between something and you'll confuse MATLAB, right? So when I've defined Y, I hit enter, and there's my 3 numbers. And you can see MATLAB has already defined each of these in Cartesian coordinates. So there's 0 real plus 10i, 0 real minus 5i, and 3 plus 0i. Since it's using complex, it goes ahead and it defines even the real numbers as complex numbers. So that's nice. And so then I just type in Wye-Delta, the name of my M file, and boom, there's my answer. Okay? I've got my 3 elements. And you'll see they're all very much complex. And so I can fill in my boxes. Right? The first element in the delta array, again, I now have to remember what that corresponds to. So I like to remember that the Y points at the delta element that it corresponds to. So if that was my first element, it points to 1.5 minus 5j. Element 2 points to its element, so this is negative 3 plus 10j. And then the third element points to its corresponding element, so that's 16.67 plus 5j. And that's my corresponding delta, right? Not too bad. Now, if I had a delta, I could define the delta and I get the corresponding y's. So, again, in this case, you're going to have to remember sort of what's going back to what, and again, remembering the position. So if I take this delta and I just say delta y, it spits me back out my y, right? And it should be defined now. So again, my first element was the 1.55, and that is corresponding again to my y element of 10j. And then the negative 0, negative 5i, right? That is, the negative 3 plus 10i was my second element, and that corresponds to the second element here, the negative 5. And then the last one as well, right? So they are set up so that they do correspond properly one to the other, and you can use those to go back and forth between y's and deltas, putting your complex numbers in. And then also if you are, like if I'm doing this, I may not want to rewrite all of these. So remember, these are arrays. So you can access one element of that array to use in another calculation, right? So if I wanted to get just this element right here, this top 16.6, that was in my delta, and that was the third element. So if I look at delta 3, and I put that in parentheses to call that index, it pulls out just that element for me. So like if I did a Wye-Delta and then I needed to do some series or parallel combinations with some of those elements that resulted, I don't need to retype those values. I can just use and say, oh, that third element, delta 3, right? If it were, if I did the Wye-Delta because then I had another impedance up here that I wanted to make a parallel combination with, right? I can just call out delta 3 and put that in parallel. And so remember, I have that parallel macro or function defined. That's defined as a function, so you actually have to pass it the values. So let's say, well, let me write it down to a number. So if this is 2 plus 3j, and I want to put that in parallel with that third element, I would use the LL command. And so I could say that, z equals LL, and you have to have parentheses to pass the argument to the function, but then the argument you pass is a matrix. And the matrix, or the array, are the various elements that I want to have in parallel. So in this case, I want to put, I have to have my array, and the elements of the array in this case are delta 3. So the array includes an element of an array, right? And then the other element, I'm going to use parentheses just to identify, what do I write there, 2 plus 3j. And then hit enter, and it calls out my result, right? And stores that result in z. So that's the benefit of a function as well, right? Versus a script, versus the standard M file, is that the function returns a value, and so you can assign that value to the variable name. So that's a little different. But writing the function is a slightly different notation. So I think you guys covered all, in MATLAB class, you all covered writing functions, right? As well as M files, scripts. So you haven't seen it, Justin, but just to flash it, so right. So you actually have to do a declaration statement. So you actually have to tell it it's a function. Whereas the script, you literally just write the commands that you would type into the command window. The function is a little bit more like programming. You have to define the function.
And you write comments about it as well?
Well, you should always comment. Even in the script file, you can do a comment. So that's just with the %sign. And so then, yeah, just define your function. You say, okay, I'm going to return this value. So the function returns this value. And then this is how you call it. So that's the name of the function and then its arguments. And then how you use the arguments and everything, that all depends on what you then define down in the bottom. And using semicolons suppresses the intermediate outputs so that you just get the final result that gets returned.
Gotcha.
So again, slightly more complicated than writing a script, but it gives you the flexibility that you don't have to predefine your arrays and all of that kind of stuff. Whereas with the Wye-Delta, you have to have it in an array called delta, right? So it's, if you think back to your programming classes that you've had, when you're doing because you guys have done like SW131 now as well. So if you think back to programming classes, the differences between local and global variables. Scripts operate on everything as if it kind of were a global variable. You have to just have it defined in your workspace. The function, you can assign and do things down in here, and they're just within the function, and those never get returned back to the workspace, right? They just live there temporarily. You return your one value, and those things are gone, right? And so it doesn't matter what I call them, or if I've reused a name or something, but those global variables, scripts are operating on those, the things that live in your workspace. Okay. Any questions? While I got MATLAB up and running, and no? Everybody good? Do you guys have these still installed in your MATLAB folder? Yeah? So you guys should do that if you haven't already. And very, very handy, like I say, for the complex stuff. Just to show, I think I mentioned the syntax. If you want to use it, you can do the cart to pull or pull to cart. So if you do the pull to cart command, you have to define the array as x, comma 1. That's what I want returned back. And that equals pull to cart. And you put in your two elements, which will be your theta and your r. And I think they go in that order. So we had that one, I don't even remember the value, but let's say we had negative, I don't know, 3, it's in radians though, so theta in radians, I don't know, so say, I don't know, pi over 2 then, it'll be 90 degrees, right? And then the actual length of the vector, we'll say it's 5. So this is a 5 at 90 degrees, so this would be J5, right? That's what we should expect to get out. Oh, sorry, minus pi over 2, so negative J5. So when I hit enter, it returns X and Y. Maybe I had those in the wrong order then. So I thought it was negative pi over 2 length, and 5 is the phase.
Is it a parentheses thing?
No, negative pi over 2. Why is it giving me, oh, I'm sorry, it's e to the negative 16. That's just rounding to 0.
Wow.
Threw me off for a second when I saw the 3, but I didn't read the rest. But there's e to the negative 16. That's as close to 0 as MATLAB can get, obviously. So it's
Weird value.
yeah, 0 and then negative. So I put them in the right order. So it's negative 5 on the J-axis, right? So you can use those, and it loads the real and the imaginary parts. The thing is it loads real and imaginary parts into separate variables, which makes it a little bit more complicated to work with, in my opinion, and that's why I use those absolute value and angle functions more. So, anyways, all right, guys. So we'll see you on Monday. Provided there's no snow. There's snow planned for 4 days next week, and I don't think it's supposed to be too bad, but since we've done the Blackboard Collaborate, should we end up with another snow day, plan to just log in and do it that way instead. So, all right. See you guys. All right. Now I can